Hi there, welcome to this lecture series on matrix algebra. This is lecture 31, part 1. The topic is positive definite symmetric matrices. We'll cover positive definite matrices and the quadratic forms, and also introduce the Sylvester's theorem. Let's get started. In the previous lecture, we learned the connection between a symmetric matrix and a quadratic form. So quickly summarize, a quadratic form can be represented uniquely with a symmetric matrix. So for every m by n symmetric matrix A, let's say Aij is its element. So this is symmetric, meaning half of the entrants are unique, the other half are just symmetrically same as the early half. And then this corresponds to a quadratic form in the variable x1, x2 to xn. The quadratic form would be x transpose times A times x. If one writes out the components, then x transpose is this row vector, and A matrix is this matrix here, and then x is the column vector. And we know that this multiplication, so this one multiplied by this matrix, you will get a row vector, and then multiplied by a column vector, you get one number. And one can also write out in components that will be a double summation and over all possible combinations of Aij times xi times xj. So the question here we want to ask is the following. What can we say about the sign of this quadratic form? Does it take a positive value always, or a negative value, or sometimes? So it turns out that the sign of the quadratic form is of much interest, and we have a definition on various cases. So here is the definition. So this is the quadratic form, and we say that the quadratic form Q, as given here, is various cases. Let's go through the first one. We call it positive semi-definite if Q of x is bigger than or equal to 0 for all x in Rn. And now if we change the bigger than equal sign to be strictly bigger than 0, and then this is called positive definite. So this relationship holds for all x in Rn, for all x that's not a 0 vector. Because, if it's a 0 vector, this is always 0. So if x is not 0, and then this Q here is strictly bigger than 0. And then if the Q can take both positive and negative values for different choices of x in Rn, then we say this quadratic form is indefinite. And now we have the counterparts for the case when this is negative. So if Qx is less than equal to 0 for all x in Rn, and this quadratic form is called negative semi-definite. Semi means that it can be 0 for some x that's not 0. And the last one, if this is strictly less than 0 for all x that's not 0, then this is called negative definite. So this is the opposite case of positive definite, and the negative semi-definite is the opposite case of positive semi-definite. Now, since we have established a unique relation between a quadratic form and a symmetric matrix, then we would use the same definition on the quadratic form to the symmetric matrix, and calling them the same term when similar things hold. So let's go through this. So we say that we have a symmetric matrix A. We say that it's positive semi-definite if this here, this is actually a quadratic form. So if xt times a times x is bigger than or equal to 0 for all x in Rn. And then if this is strictly bigger than 0 for all x that's not 0, then we call it positive definite. And the rest is all similar. And then if this one can take both positive and negative sign, then we say the matrix A is indefinite. And then there is the negative semi-definite for the A matrix if this thing is less than or equal to 0. And then A is negative definite if this is strictly less than 0 for all x that's not 0. Okay, so all these conditions on x are similar, and then we give the same names to the A matrix as the names we give to the quadratic form. Let's take an example. So we have a matrix A, which is symmetric. Let's do a 2 by 2. And then we can write out the quadratic form, x transpose times A times x. And if we put in the numbers, we can work out, and this becomes 4x1 square coming there, and 10x2 square coming from here. And then this one is the sum of these two, so I get negative 12. Can we show that this matrix or this quadratic form is positive definite? Well, indeed, we can show the quadratic form directly by manipulating the quadratic form into two terms, the sum of two terms, which both are positive. So we can make a square using the first two terms here, and we see that if we add 9x squared, we made a square. So this will be 2x1 minus 3x2 squared. So once you've taken the 9x1 out, and then we totally had 10, so there's only one here, so 1x2 squared remain. So we have the sum of two terms which are both squares, so these are strictly bigger than 0 if these x1, x2 are not all zeros. So one can also visualize this by making a surface plot of Q, and in the 3D plot, so down here is x1 and x2, their value, and the z-axis will be the Q value. And if you can use any program to plot this surface of this, and then you will see that it's a parabola, and it has a minimum point. That's where x1 and x2 are both 0, and that point it touches the origin, so it takes the value 0, and the rest is all above 0. Let's take another example. So here is the A matrix, like that, and we can write out the quadratic form, which is this: 9 come from here, and 1 goes there, and then negative 3, add negative 3, we get negative 6. We want to show that this is positive semi-definite. And looking closely at the quadratic form, we see that what we have here is exactly 3x1 minus x2 squared. If you open this up, you exactly get that. So that's the qx. So this guy here is non-negative, so it's bigger than or equal to 0. And it is not positive definite because it can be 0 even when x1 and x2 are not all 0. So we see that if 3x1 equals x2 here, but x1, x2 are not 0, then this quantity is 0, and then we will have the quadratic form 0. So therefore this is only positive semi-definite. And we can also plot this and visualize the q of x and the surface of the q of x. So qx is in the value is in the z-axis, and then we have x-axis, x1 and x2. Okay, so when x2 equal to 3x1, that is represented by this red line in this surface formed by x1 and x2. Along that line, and q of x is 0, so it touches the 0 level surface, and then the rest is this parabola. And you can think you have this parabola, and you move this parabola in this direction along this, keep the tip along the red line, and then it forms a surface, and that is the surface plot for qx. So you see it takes value 0 even when the point is not at the origin. One more example. We have this matrix 2, 1, and the 5 and the 5, and then we can write out the quadratic form, which is here. So 2, 1 goes here, 2 and 1, and 5, 5 makes 10, and it's here. So we want to show that this is actually indefinite. Then to show that it's indefinite, it is enough to find some different values of x1 and x2, where the q is positive for some choices and negative for the others. Then it's indefinite. So we can just try our luck and try a few numbers and see what comes out. So if we put in 1 and 3, and we see that we get 41, that's a positive number. And then we see that this 10 is bigger than 2 and 1 here. So if we can make x1 times x2 negative, we'll get a pretty big negative number. Indeed, if we put 1 negative 1 here, then we get this, and it's negative 7, and it's less than 0. So this quadratic form is indefinite. So here is an illustration of the surface plot, typical for this situation. So at the origin, and if you look at in the x2 direction, this is, if you just like make a cut and look at this line, then this line has the minimum at the origin, and then the rest is positive. But then if you cut a line through in the other direction there, then you see you get some curve like that moved down here. So it has a maximum at 0 and is negative in the remaining part. So a thing like this, a point like that, is usually called a saddle point, but that comes later. So I just want to put the name out there. Okay, so you see this surface, part of it is above 0 and part of it is below 0. Okay, so we can also get some examples where the quadratic form is negative definite. Let's look at matrix A like that. And the quadratic form would be this one. So 4, negative 13, 6, 6 is 12. And now let's see, how can we show that? Well, we can do a similar trick, that is, try to make this into sum of two terms that are both negative, which means they should be negative of something squared. So looking at the first two terms, 4, negative 4 and 12, if we take out a negative sign, then we get 4 and negative 12, and then we see that if we add a 9x2 square, and then this becomes a square in the bracket. Okay, and then here's negative 13. You take out a negative 9, then you get a negative 4. Okay, so we get these two terms, and then we write the first term as its square. So 2x1 minus 3x2 square, and then minus 4x2 square. So we have two terms, and they are both negative. Then the whole thing is negative. Okay, so this can only be 0 when x1 and x2 are both 0. So for the case you're off that point, this is strictly negative. And if you realize the surface graph of the surface for Q, and it typically looks like this. It's like a parabola going downward with the top here. The top touches only at the point where x1 and x2 are both 0, like the origin here. Okay, so we now would like to know, when is a matrix positive definite or other things, or these definite? Because what we have done through the examples are just like guessing, so we would like to have a systematic way to do this. So let's look at it. So we have a symmetric matrix A that's related to the quadratic form. Okay, and for this matrix A here, because it's symmetric, then we can always find an orthogonal matrix P such that you can diagonalize A with this P. So P inverse times A times P is a diagonal matrix. And then we can introduce a new variable. We have talked about this in the previous lecture. And the variable y is defined as follows: x equal py. And then x transpose would be y transpose times p transpose. And then we also know that y can be expressed as p inverse times x. And because P is orthogonal matrix, then P inverse is P transpose. So we have this also. So this tells us that the quadratic form xtax is, if you put in the expression for xt and put in the expression for x and write everything in y, you get that. And then the middle three matrices, PTAP, is just P inverse AP, which is D. So we get that. So with this variable change, this quadratic form is the same as that quadratic form, but here the matrix here is diagonal matrix. The advantage of the diagonal matrix here is that the quadratic form is now very simple. So let's lambda 1, lambda 2 be the diagonal matrix. They are actually the eigenvalues of A that's going in this diagonal matrix. Then the quadratic form using y coordinate would be lambda 1, y1 square, lambda 2, y2 square, and plus all the way to lambda n, yn square. Now we see that in this expression, it becomes very clear that the sign of the quadratic form is determined by the sum of the eigenvalues of A. In fact, if all the eigenvalues are strictly positive, then the A matrix, this term is always positive for non-zero y's, and then the quadratic form will be strictly positive definite. And then if they are negative, it becomes negative definite. And if they have mixed sign, then this can take positive and or negative values. So it will be indefinite, and so on and so forth. So that's why now you see the connection between the positive, negative, definite part of the matrix connecting to the eigenvalue of the matrix. Okay, so this is the end of part 1. And in the next part, we'll continue our discussion on this topic. So I hope you enjoyed this part, and I'll see you soon.